we will now look at how this energy is vitally linked to our development. So before we go to that process, we are talking about our energy transition, and our course is titled Sustainable Energy Technologies, and you may have also heard of renewable energy technologies. What is the difference between these two? What is renewable energy and what is sustainable energy? Are they the same? First question. Is there really a difference between them? And how does it differ from previous types of energy technologies that have existed before? So, harnessed energy can be considered to be renewable energy if it is sourced from naturally replenishable sources. So the energy is coming from nature fundamentally. Are you taking the energy from a natural source which can replenish itself? That's the question. Okay. If the answer to that is yes, then your energy source is a renewable energy source. An example is solar energy. You are using solar cells to convert the energy in the light of the sun to electricity. Of course, the light of the sun is being consumed by the solar cells. Is it being replenished? Yes, every second, every hour, every day for the next 3-4 billion years. Sun will continue to generate light. How? Through nuclear reactions happening in its core. So it's a naturally replenishable source of energy that is being replenished every second, every millisecond. So it's a renewable source of energy. Wind energy. You are using a wind turbine and you are harnessing the kinetic energy of wind to generate electricity. How, we will see later. Is the wind getting replenished? Again, yes. Every second, every hour, new wind sources arise through basically pressure differentials that exist in the atmosphere normally, and winds continue to blow at different rates. So again, a naturally replenishable source of energy. Hydropower, flow of water. Basically taking into advantage the natural flow of rivers from the mountains to the seas that is happening again and again. Rainfall is replenishing your water source. So water is a replenishable source in that way. Another slightly controversial source of renewable energy is biofuels. Energy from natural biomass, like wood, like forest residues, agricultural residues, oil crops, etc. You can grow oil crops every year, use that oil produced from the crops to generate your biofuels like ethanol. We will discuss that. So it's a replenishable source. There are certain concerns regarding that. We will discuss those aspects. But on a first approximation, it looks like a replenishable source. Alright. So those are examples of renewable energy technologies. Technologies that harness such a replenishable source to produce energy applications that we need. That's it. Sustainable energy has a slightly different definition. It says sustainable energy is that whose extraction, deployment and consumption, three things: extraction of that energy, deployment of that energy to the general population, and consumption of that energy by the general population, so three pillars, in no way compromises the needs of the current and future generations, does not compromise the requirements of the current generation as they lead their day-to-day or year-to-year lives, and future generations, 100 years from now, 200 years from now, depending on the time span you are looking at, 3 or 4 generations. So that technology, energy technology, where the energy extraction process, energy deployment process and energy consumption process does not compromise the requirements of the current and future generations, in terms of resource availability and environment quality. So the resource is not getting depleted and the environment quality is not getting lost through the through this energy harnessing, deployment and consumption phase. These are not the same precisely because if you think of it, yes, the renewable energy source, the resource may be naturally replenishable, but maybe when you are deploying it and consuming it, you are doing it in such a way that is destroying the environment in some way. Then, even though it's a renewable energy source, the method of its use is not sustainable. Okay. So those issues then become important. Alright. Similarly, you can think of something that is sustainable but not renewable. For example, you can think of a zero carbon economy. This is kind of an important technological goal that many people are thinking of. You are using carbon in fossil fuels to generate fuels, usable oil, petroleum, etc. Running them to generate power, but you are trapping the CO2 and converting that CO2 back into useful chemicals or fuels back, which are again coming back into your system. So throughout this cyclic economy, you are not allowing that resource to be to come out of the system as a waste product like CO2. Alright. So even though your natural resource is not replenishable, since you are not letting that resource go to waste but cycling it back, then it becomes a sustainable economic system. It's not currently realizable. There is methods people are looking at. Whether it's feasible or not is another question, but still that is one idea. Similarly, as we said, renewable but not necessarily sustainable, large hydropower often lands into this kind of a controversy. You have to build a huge dam over a natural river ecosystem that fundamentally alters the ecosystem, potentially displaces millions of people because of the reservoir which inundates farmlands, forest area, etc. Breaks the natural movement of water from upstream to downstream, which fish and marine ecosystems rely on. The dam can become silted over time, reducing the capacity of the dam to hold water. That may lead to catastrophic floods or dam breakage. All of these things have happened before. So a renewable resource is being harnessed in some cases unsustainably. Right? Nuclear is another case. Nuclear is certainly not a renewable resource. If you think of uranium, there is only this much of uranium that is present in the world. But you do not need a lot of uranium. It is possible that you can, if you can store the uranium waste carefully in hermetically sealed safe containers and tackle all the issues regarding the potentiality of nuclear breakdowns, nuclear accidents, that it can become a sustainable energy source, as many people in the nuclear energy field. Because you don't need a lot of uranium, so you are not going to running out of that resource in the foreseeable future. It is not generating CO2 and other greenhouse gases, so maybe it's more better in that form in terms of environment than other types of fossil fuel systems. So it may be arguably a sustainable energy resource. There is a debate to be had on that front. The other point is, when it in terms of resource, things are either renewable or non-renewable. Solar is renewable, coal is non-renewable. Sustainability is a gradation. You can think of things like a sustainability index which you can attach to an appliance. Whether it has been sourced through recyclable materials, whether it is catering to the highly energy efficient ratings, 5-star rating, 4-star rating, etc. So sustainability is a gradation which can be indexed or ranked. It's not a on-off thing. Either completely unsustainable or completely sustainable. There is a range between them. And there are certain technologies that enhance the sustainability of a certain resource. So anything that decreases the harmful effects and that makes it easier to so that the future generation needs are not as much compromised as before is a sustainable technology development. So for example, energy conservation. If you conserve energy, you need less of it. So it's a sustainable technology process. Improving energy efficiency is a part of sustainable energy technology. Energy efficiency is you generate the same work but with less energy input in the first place. More efficient light bulbs, more efficient computers, right? Waste to energy, as we discussed. If you can recycle CO2 and bring it back to the original hydrogenated fuel, you are shifting a potentially harmful greenhouse gas waste CO2 into a useful product. Similarly, agricultural residues can be converted into biomass and can be used as biofuels. Waste to energy. Carbon capture and storage. So again, CO2, basically it's CO2 capture and storage to prevent the CO2 from leaking into the environment as it is produced by fossil fuel technology. These are not part of the renewable energy technology basket, but are part of the sustainable energy technology basket. So it's a broader goal, correct? So I hope those ideas are now clear. So now let us look at the energy transition in society. Okay, the role of energy in today's society on a global basis. All right, and this figure is very interesting because it shows the night in Asia, and you see the light that is coming from the different regions in China, Southeast Asia and India and the Gulf area where it's just about evening now. And you see the large cities are brightly lit. You can easily identify which are the large urban areas from this map. Here is Hyderabad, very likely. Okay, here is Hyderabad, this is Bangalore. This is Kolkata, this is Delhi, this is Bombay. Very clearly identifying points where a lot of people are using a lot of electricity that is lighting up the world. Here are the major cities in China. Here is Japan, Tokyo, etc. Here is Singapore. Okay, so you can see the major cities, and you notice the wilderness. Tibet, very thinly population, no electricity, significant source of electricity. So this kind of gives you a picture of how much energy that we are consuming on a daily basis, especially in the urban centers, and how it is ununiformly distributed. Not all regions are using the same amount of energy. This is a figure from ourworldindata.org. Here, you should definitely take a look into this website. It's very well curated and it's lots of interesting information about the state of the world in many different dimensions. Okay. So this graph shows the energy use per capita. So per capita is per person. So how much energy is being consumed by one person on average per year. So I am consuming a certain amount of energy over this entire year. What is that amount? Okay. In the units of kilowatt hours. We have already heard of kilowatt hours. Alright. And this is the GDP, the gross domestic product. You must have been familiar with it. It's a very common metric of development. It basically gives you the amount of economic activity and its value that is happening in a country. Alright, the GDP of your country, and then you divide it by the total population of the country. So the economic activity on a per person basis. So that helps that a more populous state will have more cumulative GDP because there are still more people in it. So if you do a GDP per capita, it becomes a better measure of the amount of economic activity that is happening in that country. All right. So this is 2015 figures. I could not find a more recent figure, unfortunately, but still relatively recent. All right. Energy use per capita, GDP per capita. So this is India. The mean energy use per Indian is around what 7,000 kilowatt hours. Okay, and the mean GDP of India on a per person basis is around $5,000, 2015 values. All right, this will have increased to some extent by 2023, but gives you a snapshot. Here is Bangladesh, much lower energy use, somewhat lower GDP. Here is Pakistan, somewhere below us here. Philippines, Indonesia. Here is the world average. Combine the GDPs of all countries, combine the total energy use, total divided by the population for both cases, and this is the average world GDP, which is around 18,000. So around 3.5 times that of India, and the average energy use 20,000 kilowatt hours per person, which is again very similar, 3.5 times that of India. Why? Because we see this trend. As your country's economic activity intensifies on a per person basis, the energy consumed by the country on a per person basis also increases linearly. This is a logarithmic chart, so just be careful. This is a log. So it's basically still linear. I have done a log to better show the results, but you have a kind of a linear line going. As your economic activity and the development of the country increases, the energy use per capita also increases proportionally. Alright. So here at the very edge you have your developed countries. High economic activity, more than what? This is 50,000, I am hoping. $50,000 is the average GDP activity here of North America, South Korea, Netherlands, Japan, UK, Hong Kong. The energy use per capita is around 50,000 kilowatt hour per person. Somewhat higher for some cases, 100,000, somewhat lower up to 30,000, 40,000. Okay. So you can see quite clearly, I hope, that yes, there are differences. So USA consumes a lot more energy than say United Kingdom, though the level of development is very similar. So energy efficiency metrics do matter. So that is one point we will discuss later. But very broadly, greater development means greater energy use per person. Okay. And this means especially, so this blue is China here. Okay, so it has caught on with the world average in general. India is slightly distant. So as India moves up, China moves up, the world moves up in even more economic development in the next 100 years or further. It is expected that the amount of energy we will be consuming is going to increase at a per person level. Okay. Now think of this combined with the expected growth in population. Population of the world is growing, population of India is growing, and the growth will continue till 2070, 2080 and so on. So clearly in the next 30, 40, 50 years, you will see very large growth in the cumulative energy use per person and per person energy use, particularly in the developing world countries like India, which has a lot of growth still to achieve. Clear? So this is a very important point to be noted, and something that creates a challenge because sustainability issues comes to the fore when we want to increase the energy consumption. Right? So I will, this is another level. So this is energy with human development. index. So Human Development Index is an index developed by UN and some other NGO organizations that is not only looking at the GDP per capita, which was what we were looking at before, but also the education levels, how many years of schooling, expected years of schooling, health, life expectancy and birth, and other indicators, and develops a combined matrix of the level of human development in certain countries. Not only the economic growth, but growth in knowledge, in education, growth in health sector, etc. Okay. So it's more of an inclusive kind of a growth they are looking at. And compare this by per capita primary power consumption. So kilowatt per person. So obviously that was kilowatt hour in terms of the entire year. Here this is amount of energy consumed per second by a person in that country. So that is what is being shown here. And here you see initially there is a very steep rise of primary power consumption with Human Development Index. So India's Human Development Index is around 0.55, 0.6, something like that. Its primary power consumption is around 2 kilowatt or 1.5 kilowatt per person in this very steep slope. So, here are more underdeveloped countries like Niger, Afghanistan, etc., which have much power consumptions are close to say less than 1, and they have very low Human Development Index in these cases. So as the power consumption ability of a country per person increases, its Human Development Index rises very steeply to kind of the middle income countries like Brazil, China, Mexico, Portugal, etc., which are kind of what are called the mid income country levels. All right. Then it starts to kind of track a little bit differently. Next, the Human Development Index kind of begins to flatten out and no longer depends as much on the amount of extra power being consumed by a person in that country. Alright. So GDP growth is linear, but the other growths kind of flatten out. Power no longer makes that much of an impact, and hence the effect kind of stabilizes. So here you have Germany, South Korea, Russia, and other European countries here, which consumes reasonable amounts of power, around 5 kilowatt per person, but have very good Human Development Index of around 0.9. You go up to more energy guzzling countries, USA, Norway, UAE, Iceland, etc. Their Human Development countries are at the same level, but they consume a much more power on a per person basis. So here it no longer matters that much. So if you look in this context, then maybe we can think that a developed world measure of Human Development Index can be achieved with per capita power consumption of about 4 to 5, okay, which can be a reasonable objective for countries like India. So this lecture I will kind of stop here. We will continue the lecture in the next class. So in this lecture we looked at units of energy, we looked at energy and its overall role in society in development. In the next we will look into how the energy growth in various sources, uses has changed in the last 30-40 years. Okay, the macro energy trends in the world. Okay, so thank you for listening and hope you enjoyed the class. Let me know if you have any questions on the websites, and we will definitely try to answer those as and when needed. Thank you and hope to see you in the next class.